My talk is on the operator is the model. So I'd like to present to you a point of view, really, which I hope is going to put the aspects of things that we're doing in a slightly broader context. And actually, many of you might have already thought about this, this particular idea, but let me go through it and then show you some of the technical aspects of it that I thought about, and then we can discuss from there. So I will start by doing some history and setup that pretty much all of you know, but just to put things in context of what I'm going to say next. Then I would like to talk about a concept of representations and learning of representations. This is just putting the Koopman operator theory in the context of the underlying system and learning of that particular system. Then I'll say something about spectral theory on functional spaces, and this part is going to be hopefully interesting because of the fact that most of the work that we have done so far is in spaces of square integrable functions, so L2, and I'm going to discuss a little bit further on more interesting function, well, maybe not more interesting, but broader functional spaces that incorporate L2 in its description. The invariant subspaces and representations, you'll see that the spectral theory informs us on what kind of representations we can have, and in particular linear or nonlinear. And therein is going to be the idea that we can have nonlinear representations in Koopman operator theory. And then I will just briefly talk about an application that is particularly fascinating to me, but Erwin Kamenar here is going to speak about it tomorrow. A difficult field of study, soft robotics, in which the equations are unknown, and therefore the operator is the model, in the sense that we start with the operator and try to represent it. So that's the plan. If anybody's interested, there is actually a short paper in SciAm News on this, and there is an archive paper as well, relatively short, that is a little bit more technical than this. Okay, so let's start with the basic history. We have observables on the phase space M. We have the Koopman operator that is called composition operator. M is going to be my state space. U goes from some space observables to itself. Important thing, it needs to be closed. I'll comment on this as we go. And continuous time, it's also a composition. ST is my flow for a particular continuous evolution. Bernard Koopman, who probably should be known a little bit better than he is, was a mathematician at Columbia University. He produced a fascinating opus of things, including operations research, where he is very, very famous, and then search theory, which is within the context of his operations research. Actually, in the Second World War, he was part of the submarine search effort. Karleman, so another very, very well-known name, in 1931 writes a paper that does the Karleman linearization. He basically uses the idea that Koopman also came up with, which is instead of dynamical system itself, he considers an infinite dimensional embedding of the dynamical system. Koopman and von Neumann in 1932 studied dynamical systems with continuous spectrum. If you want to see where is the first proof of existence of a chaotic dynamical system, it is in that paper. Look it up. They prove that there is a dynamical system that has continuous spectrum and therefore mixing dynamics. That actually is in this paper, and it was done using Koopman operator methods, which I find fascinating because we of course all celebrate Lorentz's 1960, Ueda's 62 and Lorentz 1963 advances. That turned into an ergodic theory adventure, and then in statistical mechanics, Morians once again used similar sets of ideas in order to do physical chemistry. The idea was you want to define the system on some low-dimensional space with some variables, and then you project, and the rest of it you can sometimes model in very high-dimensional systems with stochastic dynamics. So what we were interested in to start with, and I don't know if you've seen this video or not, but that's a jet coming out of an orifice. You've seen it in real life in the sense that smoke coming out of the chimney looks exactly like that. But the point of it, it's a three-dimensional flow, very complex contours of streamwise velocity. That's one contour of streamwise velocity, and the question is, the question asked was, well, can we do anything about deciphering the internals of this motion? It looks very chaotic. The question is it really? So in the vector field case, the situation is quite simple. You have an equation x dot is equal to f of x. If we have control, and I will speak about control a little bit, you add a term that depends on the control. This is a slightly simplified, but basically is in essence correct. You have the generator equation, f of x dot grad f is really the generator. If I find a function phi such that f dot grad phi is lambda phi, I have an eigenfunction. The level sets of those eigenfunctions are going to give me geometry of level sets. This is from a very, very early paper. This is about a later edition of a theorem from an early paper where you find invariant sets of kicked pendulum. So for those of you that recall the studies of standard map, this is actually the ergodic partition of the standard map. But today we are going to speak, a lot of us, I think all of us, are going to speak about dissipative systems. And so in dissipative systems like van der Pol oscillator, we have the limit cycle and you have the off-limit cycle contraction dynamics. And so the question is, how do we deal with those kinds of systems where we need to find the description in the full state space in the basis of attraction. And I did show you this initial movie just to point out how complex the dynamics is. Interestingly, so this is a paper with Clancy Rowley and a few other collaborators. Interestingly, when we computed this, we found that the spectrum of the Koopman operator, so found right there with those lambdas, is on the unit circle. Largely, there were a little bit off unit circle things, but there were these two red dots and then these two red dots, and they corresponded to spatial shapes that looked like that. Lo and behold, these spatial shapes actually corresponded to the physics. It's just that part of the dynamics that was not understood before we did this paper is that, for example, these stringwise vortices close to the wall are oscillating at the same frequency and they're part of the same mode as these vortices that are on the jet itself. So you can discover new physics. You can also discover invariance. If you actually look at this equation here, if lambda is equal to 0, the equation just states that f dot grad phi is equal to 0. We of course know the most famous invariant in the history of the world, which is energy. If we don't have any dissipation, it satisfies that equation. So the point that I want to get across is that somehow the operator actually contains physics. It's not very dissimilar to the situation in which one studies vibration with x dot is equal to ax and finds that the matrix A, its eigenvalues, actually contain physically relevant quantities. There is no a priori reason for this. There is no a priori physics that says eigenvalues are going to be an interesting thing, but it so happens that they are, right? So this is the unreasonable effectiveness of mathematics in natural sciences, as they say, that an object that is abstract actually contains the physics that is interesting. Okay. To a certain extent, that's why we are all here. Because if it doesn't, then probably the interest wanes after a while. And the standard problem in machine learning right now, in the context of neural networks, is what is a coefficient? What does a coefficient mean? What does an object that we have computed actually mean in human language? In the paper that I have shown you, I actually make the case that it is perfectly fine to compute with these kinds of, with that kind of machinery. What we need to have is a language by which we understand what the machinery has told us, and therefore parsimonious models that actually describe what we are seeing, right? So if we are to have any hope of a human-machine interface, we need models that parsimoniously describe what the machine is telling us. This is not a statement against machine learning the way it is done in the context of deep neural networks. It's a statement about the reality of humans interacting with machines and trying to understand what they have. In this context, we do have objects that we know about. Okay, so that was the part that described a little bit of history and stuff. I will go very technical now and tell you something about how do we describe spectral expansion for composition operators when we have dissipative systems. So in my view, the proper setup for this is the setup of what is called a Milnor attractor. I will reference the figure that I had here. So here the attractor is in blue. Everything converges to it. What you're seeing here is the level sets of the Koopman operator, the described geometry. I'll get to that. So, in general, I can consider a compact forward invariant set of the flow. I'll ask for a physical invariant measure. The only thing this means is that when time goes to infinity, the time averages of any continuous functions are equal to the averages with respect to that measure. If you know about statistical mechanics, it's the same kind of assumption just for dissipative systems. These are called Milnor attractors. I can take a Hilbert space of square integrable observables on the attractor to start with. I'm allowed to do that by the fact that we have a physical measure and all these time averages converging. I will show you that these functions on the attractor, so you could say, well, the attractor is a very low dimensional set, but I will describe how you can expand them to the whole state space, and this is the crucial part of the construction. And then I'll construct HB as a subset of all continuous functions on the domain, in particular the ones that vanish, on the attractor as a Hilbert space. So note that I have somewhat defined HA. I haven't defined as well HB. I left it kind of open. I just said it's a subset of continuous functions that has a Hilbert space structure, so we'll talk a little bit about it. I need to append the constant. If you're doing a tensor product of spaces, let's say space X and space Y, then you take all the harmonic functions on X, take all the harmonic functions of Y, but you need to have them separately, so you need to have a constant in your set of functions in order to be able to represent all the functions on the product space. So that's the reason why there is this appendage of one. So now, if you have a bounded operator on some space, we call it a scalar type if you can expand it like this. For matrices, this is just the sum over eigenvalues and projections which are just the projections of eigenvectors. So it's a discrete sum. In the operator case, it's an integral over the complex plane. The tensor product space is the product of functions on the attractor that are defined on the attractor and off attractor. If I assume that the whole space, I need to prove this, that the whole space, Hilbert space, is invariant under the Koopman operator, then so is HB, so I don't need to worry about that part separately. Clearly, I can have a separation of the operator acting on HA and operator acting on HB. If I define the P of AB to be just the pointwise product, again a tensor type product of any scalars A and B in the complex plane, then this thing here is the union over all A and B of the products. Okay, I'm going through my definitions, and so here is what one can actually get out of this setting. If you have that product space, then the theorem essentially says that the Koopman operator UT, this is in continuous time, can be represented as integral over R. The omegas are in R. Think of the imaginary axis. In the discrete case, that would be the unit circle. And then Z's, so these are I 2 pi omegas are on the imaginary axis. They are associated with the evolution on the attractor. This is stationary dynamics. The Z itself is a dissipative part. It can of course be complex or real. And now you see that all the eigenvalues here are associated with the sum of Z and I 2 pi omega. So very, very simple structure. So what would that mean in the case of van der Pol? You have this attractor, you find two eigenfunctions. So these dp's are projections on eigenfunctions, just like in the discrete case there will be projections on eigenvectors. You have linearized the system with a complex eigenfunction with eigenvalue I omega. That eigenvalue corresponds to the rotation on the limit cycle. Lambda is real, that corresponds to decay towards the limit cycle. But look, we have linearized this highly nonlinear system, and here are the level sets of each of the eigenfunctions. In the red are the level sets of the phase, physically, and we call them isochrons. And in black are the level sets of the real eigenfunction, and we call them isostables. Initial conditions jointly go to the attractor along isostables, to just kind of expand or contract together. And the phase itself is the rotation phase. In effect, the Koopman operator has given us adapted polar coordinates to a nonlinear limit cycling system, in which the system appears linear. You can do this for much more complicated attractors. Milnor attractors can be quite general. Here is another system that is, in these 2D, decays to a fixed point, but then it has a phase, so it spins. So as I said, if you have a spin, or any stationary dynamics, is going to show up in eigenvalues on the imaginary axis. In this particular case, the lambdas are plus minus I. So if you have that, the eigenvalues on the imaginary axis are going to be n times that. But then you have another set of eigenvalues that are complex conjugate, and they are these two. And in order to get all the eigenvalues, we need to sum them up over integers in those kinds of spaces that I have just described. Right? So in that case, you get this lattice in 2D. And if you think about it, now we're getting experimental, because in spectroscopy, if I was just seeing the frequencies aligned like this, I would immediately know this is a limit cycling nonlinear system. And nonlinear because it just doesn't have just a single omega, but the harmonics. In the dissipative case, if you see a lattice like this showing up in an experiment, you immediately know you have a system that decays to a limit cycle, and it has a dissipative elements that are described by the left part of the complex plane part of the lattice. So to a certain extent, these theorems give you an experimental device, experimental analysis possibility in the same way that the Fourier analysis does for quasi-periodic systems. All right. For a large set of systems, this was initially described in this paper in 2005. You can split the dynamics into point spectrum and continuous spectrum. This is going to be important in what follows. The first term in the expansion is actually, again, physical, is the time average of your set of observables G. The Z and X are respectively the position in the space, that will be position in a three-dimensional space here. X is the position in the state space. Right? So now you have a spatially extended system, and you can decompose it as the coherent part. Lambda J's can be on the imaginary axis, off the imaginary axis. And then there is this continuous spectrum part. We very often find papers in which the continuous spectrum part is neglected, maybe for some good reasons, maybe for some wrong reasons, but it's neglected very often. It really shouldn't be. It's an essential part of dynamics, as is very clear from this. It is very clear that the dynamics is not just the sum of these two modes, but there are all these pale pink modes, some of which might be quite relevant and describe the continuous spectrum. There's going to be, I think, quite a bit of discussion on continuous spectrum with some of Matt's work and other work. Peter Schmidt developed a DMD algorithm in 2009. This was not related to Koopman. This is the paper in which things were connected, but only through spectral expansion. Today we have a much better handle on all the connections between extended DMD and Koopman are. So we know much better, and I'll say something about it. I do want to point this out without going into any details, that if you actually go into stochastic process theory, one would consider this particular expansion as a spectral theory for non-stationary processes. So I think a lot of you have seen stationary process analysis. In the context of stationary process analysis, there is a Koopman operator, well known. If you actually look back at books by Feller, Doob, and others, you will see that they clearly understood the connection between the measure-preserving dynamics, which is essentially a realization of a stochastic stationary process, and the operator theoretic part. This set of theorems gives you ability to actually speak about non-stationary, so stochastic processes that have non-stationary dynamics, that have transient dynamics, that have exponential instability or stability. So, it's a side remark. For which class of systems can we do the decomposition that I just mentioned about, which is, gives you eigenvalues on the unit circle? We dig into some classical dynamical systems theory. The cell type attractors have a splitting. They look very much, they are skew product systems. U dot is omega of U, describes the dynamics on the attractor. Y dot is A of Uy, describes the dynamics of the attractor. If you go back to the linear description here, that ends up being very simple. On attractor dynamics, off attractor dynamics, and in this particular case, the on attractor dynamics doesn't show up in the linear description of off attractor dynamics. In general, it can, but that's what we have. And so, after all this development, we can define something that's called a modified Fock space. What is this Fock space in general? So, assume that you have a real line, and you put a density on it, so a measure, that is Gaussian, e to the minus z squared over 2. And you have a dynamical system, and you ask, if I take a function in that space, so remember you have a Gaussian density, so any polynomial is going to be in that space, right? So you ask, well, which dynamical systems make that particular space closed? And you find that none except for linear. It's really interesting. So this is a result by Putinar and a few other people. So I was talking to Mihai Putinar, who is, for those of you who maybe don't know him, but there is a class of Putinar operators, so he's a very well-known functional analyst in Santa Barbara. And he said, well, these Fock spaces are good, but they don't close under the Koopman operator. So it's interesting because if you have a linear system and you can conjugate to a linear system, then maybe the conjugation is going to give you something. So instead of defining your space with respect to the original variable, let's call it z, that only closes in a linear system, you define it with respect to a conjugacy. So if you do that, if you want to do that, you need n functions that are principal eigenfunctions of ut. They are the ones that generate all the others. The eigenfunctions in this case form a group, provided there is invertibility condition, so a little bit technical side. But if you do that, then you can use these functions in a Gaussian-like density. So instead of the original coordinates, you're using a Gaussian-like density, and then you're using your f's, composition with s. You're basically doing a conjugacy to a linear system and then providing a definition for this space. It happens to be, this is off attractor part, it happens to be a reproducing kernel Hilbert space that is closed under the dynamics, right? So that's quite nice, because there is some debate going on that says, well, why do you work on L2 spaces? You cannot assess pointwise elements of these, because they're classes of functions, right? Pointwise evaluations. This is a fundamental misunderstanding of Birkhoff's ergodic theorem, which is absolute magic, that says, okay, even if you're in L2, if you sample along trajectories, you will get the correct value of the average, despite the fact that you cannot evaluate the function at a point. This gives us ability to compute in L2, just like sampling theorems always do, right, in dynamical systems. But in this particular case, off-attractor, it is useful to have off-attractor reproducing kernel Hilbert spaces. And in this case, the spectrum of the operator is the closure of the products of on-attractor, so that's HA, and off-attractor dynamics, again. So in these modified Fock spaces, what I'm claiming is they're good for computation, for general attractors, right? Because you get RKHSs when you need them. Why do you need pointwise evaluation of attractor? Consider just a fixed point example, and you will see that if you're in L2, if you're converging to a fixed point, well, at a fixed point, you might not be able to evaluate. So the function can be completely discontinuous at the fixed point if it's an L2. So off attractor, you actually do need some continuity, and that's what you start with here. Simple example, x dot is equal to f of x in 1D. You find the conjugacy h, and instead of f e to the minus z minus x squared, you do this kind of a computation and have a perfectly nice space. So far about, I've talked about the functional spaces that are interesting, and these were defined in a few papers, but that's all about spectral expansion. I want to switch a little bit and talk now about Koopman Operator Theory as a modeling framework. But you will see that I will come back to what I just said, because analyzing it in the context of a modeling framework, you actually come back to the spectral expansion ideas, and you need specific functional spaces to be able to understand the ability to represent these systems. So it will look like an abrupt switch, but you will see that I will bring it back. All right. So what do we have in the general context of modeling? We have some abstract dynamical system that goes from P to P prime. Doesn't need to be defined in any reasonable way, like Poincaré way, where you have positions and momenta. It's some abstract thing. You can even consider words. People do. Large language models, there are a few papers now that consider Koopman operator theory based modeling for just switching between words. Clearly, on these words, I need to define some observables, numerical observables, right? I need some numbers to associate with them, and that's what was discovered in deep learning when transformers were pushed on, that the embeddings themselves are a good framework to work with. Not the symbolic computation, but the embeddings. So I will say that was an idea that was stolen from the Koopman operator theory, right? The embedding is the essence of what we do in this context. Not obviously stolen, they clearly didn't know about this, but they came up independently with the idea that words need to be associated with numbers, and then you need to somehow embed them in a lower dimensional space in which you can do great computation. So you have this abstract transition. Let's say somebody gave us some observables. You have x prime is equal to t of x. We expand x, that's our original set of variables, in the basis fj, can be orthogonal or non-orthogonal, and we obtain that for each fj in the basis, we have a matrix ujk that acts on it. We transition that to the same space of observables. We get x prime that is a sum over both fk's and the coefficients of the original function. I want to remark on the fact that the ujk acts from the left on the functions and from the right on the coefficients. So when you see the papers in which DMD is done, think of it as Koopman operator acting from the left. When you see the papers on which coefficients are being done, think of it as Koopman operator acting from the right. They are the transposes of each other. We have a general Hilbert space. I've defined some just in the previous part of the talk. We have a complex inner product on it. The compression of U tilde, the finite section, the Galerkin projection, whatever part you want, whatever you want to call it, in an unconditional, not necessarily orthogonal basis fj, is composed of elements that are ukj tildes, which are inner products of u acting on the jth basis function and the kth dual basis function. So the procedure is find the basis vectors, find the dual basis, find the inner products, and this Pn projection. So we're in some subspace. I might have a function outside of the subspace. I project in, act with the Koopman operator, takes me out, project back. This is standard. But I just want to say this is a general Hilbert space setting that many of you have already studied. The interesting bit that comes from this is that if you have an ergodic system, if you're studying things in L2, then this inner product here is replaced by a limit when m goes to infinity, fj composed with t, that's the u of j, multiplied with the dual basis functions. Okay, so this is actually a dramatic moment if you want to even say. Because you have to realize that when m goes to infinity, if you're sampling from a single trajectory, so real life data, I don't have ability to do multiple trajectories. It's not an experiment. I'm actually watching a real evolution of climate or weather. Then what this thing sees is only the attractor components. There is nothing else it can see. So now, if you do L2 with multiple initial conditions, everything is fine. You would replace this with some averaging over that. But what does that give us? And this is recent work with Alex Roy. So we did a little bit of analysis of that. Remember, the Koopman approximation is if you have a data matrix that is lined up like this. So I have functions, observables horizontally, and then I have the points, let's say, on the trajectory in rows. I have this Moore-Penrose inverse and then f prime, which is the further evolution. If I'm doing DMD, that's exactly the transpose. I'm saying that's this duality between acting on coefficients or acting on functions. So let's say I have a nonlinear system like this. It's a classical bifurcation system where for alpha less than 0, I converge to a fixed point. For alpha bigger than 0, I have two more stable fixed points. So here, I should have unstable points, unstable eigenvalues for this fixed point here, right? Just close to it, it's a linear system. I have unstable eigenvalues, so in the right half of the plane. For these fixed points here, I have stable eigenvalues. And I'll just remark here, if any of you were reading there are a few papers from the 90s that actually work in different functional spaces that say everything linear, so that everything is stable. It cannot be. But here is a remarkable result. This is what Alex produced. If you do standard, and this is actually multiple trajectories, EDMD with a few monomials, you get these eigenvalues that are exactly at 0. This is for the unstable case, so my fixed point is at 0. So they all only see, and this is kind of in backwards time, only see the dynamics on the attractor, right? The other ones are unstable. If you do this for a stable case, again the same thing. You're only seeing eigenvalues at 0. If you do this for something more complex, that's dear to my heart because it's modeling a vacuum. It's modeling a tube amplifier, the tube diodes. You see the spread for EDMD in these ROMs. You see the DMD, which only has 2 values here. You see the lattice of exact values. And you see this analytic EDMD that actually pays attention to the functional space of the attractor. All right. So, can I have another 5? 2, 5. To negotiate. All right. So, that's one key point. The other point that I want to make is, how can we now delineate between the systems that have linear representation, like the one I showed you, and what I would call a nonlinear representation? So let me just define a representation. If I find a set of observables f and the mapping capital F, which is nonlinear, such that this equation here is satisfied, m is an abstract point, so I have some mapping that maps f into t of m into t of m. If u acting on f is the capital F acting on little f, that's a nonlinear representation of an operator. So I just want to stress the point that typically we think of a nonlinear system and we lift it. I'm asking a different question. I'm saying the operator is the model. I know there is an operator driving my dynamics. How can I represent that operator? Can I have a finite system of linear equations that represent it? Can I have a finite system of nonlinear equations? It's turning the idea on its head, right? It is not the embedding, it's finding the right representation. And in my view, that is an interesting way to approach this whole context. It says, I have a linear operator, that much I know. How can I write it down in a parsimonious way? Coming back to parsimony. There is an interesting answer to this. So because of the time, I'll just tell you that this concept mathematically is a nicely defined concept, because if you have two different representations, let's say you have two pairs of sensors, if they are both n-dimensional and faithful, meaning they represent the dynamics in a bijective way, they are conjugates, see? So that's one result. You can have linear representations for motions on the torus. That shows you nicely that even what we would think of very nonlinear processes have a linear aspect to them. But it is a more interesting piece. So let's suppose that you don't have a linear representation. You can still have a non-linear representation of the process if you can find these functions capital F here. In the linear case, here is what the representation would be, but then if you diagonalize A, you get back to that thing that I had in the van der Pol oscillator, which is purely linear. Right? I'm talking about the generalization of the eigenproblem, where you need to find n mappings capital F that act on your observables that do exactly the same thing as an operator. We don't have any genuinely good methods to solve this. We have this, we represent them by neural networks. I tried, my students have tried. It's not great yet. So this is one of these challenges, right? If we want to have nonlinear representations, then we need to be able to solve numerically this problem. The good question is, when do we have them? The linear representation gives you diagonal things. I've shown you an example on van der Pol oscillator. The nonlinear representations show up, and this is the interesting part, when you have continuous spectrum. So, linear representations are possible if and only if the spectrum is a point spectrum, or you have a point spectrum. Nonlinear representations you can get if you have continuous spectrum, and this is the relationship that I promised on the side of relationships to the spectrum. Do I have a computation here? Erin Kamenar is going to show you this little piece of software towards the end. But yeah, you can actually identify a nonlinear representation for van der Pol, despite the fact that it has point spectrum, but just as a little bit of fun. By embedding in these three functions, you look at the matrix, you find out that it has a 2x3 block that is self-contained because x1 squared x2 depends on x2 and x1, so they need to be functionally dependent. If you find a block like that, then you will find a nonlinear representation. I was talking to Alex Townsend in Paris and asked him specifically whether there are linear algebra methods that identify such blocks, and he said that he doesn't know of any, which I believe is the hallmark for saying that there aren't any. So it's a nice problem to have. I won't talk much about control theory now because I have to finish, but I will show you this last slide that again we're going to see in much more detail of, because I want to point out what we can do today. This is in a soft arm that has LEDs on it. This is in Elliot Hawk's lab at UCSB. We're tracking the LEDs with cameras. We're putting in basically random motions that are equivalent to putting in different initial conditions. And it learns its own model, both the A matrix, the nominal part, and the B matrix. And in this embedded space, we think of it as linear. The embedding is purely by time delays. So you have 14 LEDs?
It's 16 in one case and 12 in the other.
Okay, so I was...
in this case it was 16.
I was averaging. So 12 and 16. And then we gave it a task to follow a stick. And this is what it does. It follows a stick. think Erwin is going to show a lot more. I'm not going to steal his thunder. But this last slide is to point out, look, when one has very serious theory behind their machine learning, even a soft arm composed of cloth that I've had some discussion with people who do serious continuum mechanics, and that's just very hard to model. Even in that case, you can find an embedding that allows you to control the dynamics or understand the dynamics of the device in this very, very complicated case. So you might find this example either creepy or entertaining, depending on what your position is. I think Aaron is going to give some much more fun examples. But in this particular case, follow the stick for a soft arm is the game I would like to end up with. Here are my conclusions. This picture here is just to show what I said earlier, which is, LLMs with encoders and decoders are actually very, very similar to this Koopman architecture that we are all promoting. But if you want to look at additional applications, we have some on online games, even DNN training. So I'm saying we need to find ways to interact with these models as well. Sorry for going over time, but I'll stop here and thank you very much for your attention.